All right, so this is our last lesson for our calculus. And I'm doing another bonus lesson. I'm going to introduce you to integration or antiderivatives. It's just the opposite. So what is antiderivatives? Well, I want to go back to the very first lesson of calculus that I did. And I said there was two main purposes for calculus. If we had some kind of curve, the first purpose was to accurately figure out what the slope of some tangent was on that curve. And what we did was we started by finding secants, and we found secants that became closer and closer and closer and closer, and that's how we sort of introduced limits and so on, okay, until we got to a distance between your 2 points for your secant to be 0. All right, the other thing with calculus, which we don't really do in this course, but I'm going to introduce it to you today, is if you have a curve, okay, and you want to define, say, for example, the area under this curve from, say, x equals a and x equals b. All right, so let's say here's the x-axis. So how would you do that? Well, here's what I want you to think of. What you would do is essentially find the area of a rectangle. Now that's not very good, right? There's a huge source of error right in here. So what we do is we take smaller rectangles. For example, I will take these two rectangles. Oh, sorry. I'm not very good at drawing here. I would take these two rectangles. So you can see here, I've eliminated this error. But I still have this error and this error. So what I do is I take more rectangles with a width that's getting smaller and smaller and smaller and smaller, until what I do is I add the area of an infinite number of rectangles with an infinitesimal width. And then I can pretty much say that's as close as I'm going to get, which is definitely good enough. So that's what integration is. I also call them antiderivatives because it's the opposite. So now there are two types of integrals. We have definite integrals and indefinite integrals. An indefinite integral looks like this. So this symbol is the symbol for an integral. Now, since, like I told you, we're taking the sum of an infinite number of rectangles, the integral sign is sort of like a stretched out S, which represents sum, which is what we're doing. So we're taking the sum of, say, this function, f of x, with respect to x. That's what that dx is. That's important, because you can have all sorts of functions in here, with all different variables, and what are you integrating it over? Right? And so we have to define what we're integrating it over. That's our differential. All right. Then your second type is your definite integral. This was the example I showed you. Specifically, what's the area under the graph between points A and points B on our x-axis. That's a definite integral. And I'm going to show you how to solve each one for basic polynomial functions or things like that. Okay, which is basically, you can think of the power rule, right? Or the opposite of the power rule, which is what we did with derivatives. So here we have our power rule for integrations. Let's say we want to take the integral of x to the power of some value n with respect to x. Now, if you remember the power rule for differentiation, what we did was multiply by n and then subtract 1 from the exponent. For integration, we are going to do that in reverse order with opposite operations. So what we're going to do first then is add 1 to the exponent, and then not multiply, but divide by that new value in the exponent. So that's the power rule. Now, if you had, say, the sum or difference, let's say you're trying to find the integral of two functions that are either added or subtracted from each other. You can do them separately. This is a property of integrals. So you can first find the integral of your first function, and then add or subtract the integral from your second function. Similarly, if you had some constant in there that's being multiplied by your function, you can bring that out of your integral. Okay. And last thing, you've probably seen this C everywhere. I've got like C's, I got C's everywhere, right? What's the C? Well, let's look at this. Let's say we have 2x squared plus 7. Let's find the derivative of that. The derivative of 2x squared plus 7. Well, 2x squared would be 4x. And then derivative of 7 is just 0. But that's the same as this. What if your function was 2x squared minus 4.563? It would be the same thing. It would be 4x, because this constant would become 0. Same if that constant was pi. It would become 0. So when you're going backwards, how do you know if it was a 7, a minus 4.563, or a pi? Well, without more information, you don't know. So what we do is we stick a C on the end to represent some constant or initial condition that would have been there. Okay. Next thing I want to talk about is this power rule works for any value of n except for -1. Because you can imagine if n is -1, well, when you add 1, you get x to the 0 divided by 0. But we know what the integral of x to the -1 is. X to the -1 is 1 over x. And yesterday, in our previous lesson, we learned that the derivative of ln x is 1 over x. So if you want to go backwards, the integral of 1 over x is ln x. Okay, but we're not going to do that today. We're just going to focus on doing integration with numbers that aren't, or powers that are not -1. Now notice these types of integrals that we've been doing are our indefinite integrals, the ones that could have any possible value, which is why we have C stuck on the end of it. What about definite interval, right? What about this? And we're trying to find the area between two values, A and B. In that case, this is called the fundamental theorem of calculus for definite integrals. So this is what it is. First, you find the integral between A and B for some function with respect to x. So the integral of that function, we'll just call capital F of x. Okay, that'll be our original function. And this is the notation we use. We use square brackets, and at the end of those square brackets, we write, apply this function between A and B. And to apply that function between A and B, we find the value of that function at B and subtract the value of that function at A. That is how you find the area under a curve for a definite integral. Notice that you don't need a C value in this case. You could put it in. It won't change anything. You don't even need to know what it is. And the reason is, if you have a C value, you'll have that C value for here, and then you're going to subtract the exact same C value for here. So you have C minus C. It's going away either way, right? So no need to actually worry about it. So let's try this example then. Here we have a curve. It's y equals 9 minus x squared. And we want to find the area under that curve between x equals -1 and x equals 2. So how we're going to write it will be like this. The integral between -1 and 2, so we have the definite integral of this function, 9 minus x squared, with respect to x. So this is what we need to solve. Okay, now we can pull out the 9, right? We can do our sum difference property, and we can write this as the integral between -1 and 2 for 9 with respect to x, and then subtract the integral between -1 and 2 for x squared with respect to x. That's a 2 up there. It's a terrible 2, but it's a 2. Okay. So let's start with the first one, 9. Now you can imagine that's 9 times x to the power of 0. So what we're going to do is we're going to raise that power of 0 up 1 so that we are going to have 9 times x. And then we're going to divide by that new exponent, which is 1. So divide by 1. And we are going to apply that between -1 and 2. All right, now let's look at this one. X squared. Increase the exponent by 1, so you get x cubed. And then divide by that new exponent, so divided by 3. And we are going to apply that between -1 and 2. So to apply it between -1 and 2, so the first one, what we'll do is, first, the value at 2, so 9. So substitute 2 in for x, and then subtract the value of that function at -1 in our case. So -9 times, substitute -1 in for x. And then we're going to do the same thing here. So we have 2 cubed over 3. Okay, subtract -1 cubed over 3. It's a terrible equal sign. There we go. So if you put all that into your calculator, you evaluate it, you'll get 74 over 3. Or about 24.67. So I want to talk about motion equations. So yeah, all my physics students, you're really going to love this. So take a simple example like a ball and you drop it. When you drop a ball, you know that it accelerates downwards at 9.81 meters per second squared. That's something you know. So you know that acceleration, or your function a of t, is just equal to g. Well, what about if you wanted to figure out its velocity and you just, even though I told you to memorize those 5 equations of motion, you didn't do it. But that's okay. To figure out velocity, that's just the integral of acceleration. Because we're going backwards, right? Acceleration is the derivative of velocity, but velocity is the integral of acceleration. So if we just have a g here, we just need to find the integral, right? The indefinite integral of g with respect to time, because that's what we're integrating over. All right. Well, g is just a constant. You can imagine having, say, t to the power of 0. So we increase that exponent 0 to 1 and divide by 1. So we just get g times t plus this constant c. Now in physics, that represents your initial condition. So in this case, it'll be our initial velocity. So what we have is your velocity at some time t, or you can think of your final velocity, equals your initial velocity plus acceleration times time. That's one of your equations from your 5 equations for uniform acceleration. But you wanted to find displacement. Okay, to find displacement, what we're going to do is we're going to integrate velocity. Right? Because if you integrate velocity, you get position. All right, so our equation for velocity then is a gt plus some initial velocity. Okay, this is t to the power of 1. So we're going to raise that to a power of 2 and divide by 2. So you get a half here. Here you can imagine a term t to the power of 0. So we're just going to get initial velocity times time. And then you're left with this constant. That's your initial position. That's your final position. If you bring your initial condition to the other side of the equation, you get final minus initial, which is displacement. Remember, displacement is change in position. So displacement equals your initial velocity times time plus 1/2 times acceleration times time squared. There's your other equation for uniform acceleration. And now that you have 2 equations, you can just mix and match them to get all your other equations, thanks to calculus. All right, so our first example says find the antiderivative or the integral for the following function. Here's our function. So what we want to do is find the integral of 4x cubed minus 8x plus 7 with respect to x. Now you can split this up and do the integral of 4x cubed with respect to x minus the integral of 8x with respect to x plus 7. But we don't really have to. We can just apply it one at a time because we know that rule is true. So let's look at 4x cubed. Take the cube and add 1. So you're going to get x to the power of 4. Then divide by that 4. And here we have 4 divided by 4. That's just 1. Alright, next term. X to the power of 1. Take that 1 and add 1. So you have x squared. Then divide by that 2. So you have 8 divided by 2. That's 4. Next we have 7. That 7 has an x term next to it to the power of 0. So add 1 to that. You get 7x. And since this is an indefinite integral, never, 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 never forget plus c. It's very important. Find the antiderivative or integral for the following functions. We have 5 times x squared minus 2. Alright, so we want to find the integral of 5 times x squared minus 2 with respect to x. Now remember our constant rule says we can pull that out. So we can pull the 5 out and find the derivative of x squared minus 2 with respect to x. So we've got that 5 there. It's going to all be times by, let's work with x squared. Take the 2 and add 1. So that gives us 3. And then divide by that new exponent. So divide by 3. Or if you want, you can just multiply it by a third. Same thing. Then we're going to subtract. So we got 2 times x to the power of 0. So increase it to the power of 1 and then divide by 1. And there you go. All done. So this one is a definite integral. It says find the area under the graph of 9.8x between the boundaries 0 and 5. Alright, so what we want to find is this integral between 0 and 5 of 9.8x with respect to x, of course. The 9.8 we can bring out. Right? It's just a constant. So we are trying to find the integral between 0 and 5 of x with respect to x. Alright, so the integral of x is take the exponent, which is 1, add 1 to it, so we get 2, and then divide by that 2. Or we just multiply by half. Now we're going to apply that between 0 and 5. So we still have this 9.8 out front, so it's going to stay there until the end. And we'll substitute 5. So we have 1/2 times 5 squared. And then we subtract that same function, substituting 0. With just 0. Alright. And multiply all that through, we'll get 122.5.